In this video, we will show you how to assign oxidation numbers properly. Chemists have devised a bookkeeping system to monitor which atom loses electron charge and which atom gains it. Each atom in a molecule is assigned an oxidation number, or oxidation state, which is the charge the atom would have if electrons were transferred completely. An oxidation number has the sign before the number, whereas an ionic charge has the sign after the number. Also, unlike a unitary ionic charge, as in Na plus or Cl negative, an oxidation number of positive 1 or negative 1 retains the numeral. For example, we don't write the sodium ion as Na1 plus, but the oxidation number of Na plus ion is positive 1, not positive. Oxidation numbers are used to keep track of how many electrons are lost or gained by each atom. In the case of a single atom ion, it corresponds to the actual charge on the ion. Let's start off with rule number 1. This rule states that in a formula, the cation is written first and then followed by the anion. In this example, the sodium is the cation and the hydrogen is the anion. Next, we have rule number 2. The oxidation state of the atoms in any free uncombined element is 0. This includes polyatomic elements such as dihydrogen, dioxygen, hydrogen sulfide, phosphorus, and octasulfur. Next, we have rule number 3. The oxidation state of an element in a simple ion is equal to the charge on the ion. Examples of these ions are sodium, chlorine, hydrogen, magnesium, and fluorine, which have these oxidation numbers since this is the charge of the ion. Rule number 4. This rule states that the sum of the oxidation states of all atoms in a neutral compound is 0. Example, sodium chloride, water, hydrofluoric acid, and carbon dioxide. Example for water, hydrogen is 1 positive and oxygen is 2 negative. 2 hydrogens make 2 positive and oxygen, which is 2 negative. That makes 0 as the oxidation state. Rule number 5. In a polyatomic ion, the sum of the oxidation states of the constituent atoms is equal to the charge on the ion. Examples are hydronium, acetate, ammonium, sulfate, and phosphate. In hydronium ion, the charge of hydrogen is 1 positive, which makes it 3 positive, then oxygen has 2 negative. The overall ionic charge is 1 positive, so the sum of oxidation states is equal to the charge of the ion. Rule number 6. Fluorine, the most electronegative element, has an oxidation state of negative 1 in all its compounds. Rule number 7. Hydrogen has an oxidation state of positive 1 in compounds unless it is combined with metals, in which case it has an oxidation state of negative 1. In sodium hydride, hydrogen is paired with a metal, so the charge of hydrogen is negative 1, and the charge of the sodium is positive 1. And in nitrogen tetrahydride, nitrogen has a charge of negative 2, while hydrogen paired with a nonmetal has a charge of positive 1. Next, we have rule number 8. With nonmetals, oxygen, the second most electronegative element, usually has an oxidation state of negative 2 in its compounds. However, there are exceptions in this case. There are 3 cases. Number 1. Oxygen has an oxidation state of negative 1 in hydrogen peroxide and in other peroxides, which contain the O22 ion. Examples are calcium peroxide and in sodium peroxide, which is a strong base. 2. For superoxides, oxygen has an oxidation state of negative 1/2, which contain the O2 negative ion. Examples are potassium superoxide and rubidium superoxide. Potassium has a charge of positive 1, so the oxygen atom must have a charge of negative 1/2 to make it 0. Number 3. When combined with the more electronegative fluorine in OF2, oxygen has an oxidation state of positive 2.
Lastly, we have rule number 9. The positioning in the periodic table helps in assigning oxidation numbers. Here we have the periodic table, which contains elements from group 1A to the noble gases. First, hydrogen will always have a positive 1 oxidation state when combined with other compounds, for example, water. Second, elements in group 1A, lithium, sodium, potassium, rubidium, and cesium also have oxidation states of positive 1. Examples are potassium chloride, sodium hydride, rubidium nitrate, and potassium sulfate. Third, elements in group 2A, beryllium, magnesium, calcium, strontium, barium, and radium have oxidation states of positive 2. Examples are calcium chloride, magnesium hydride, barium nitrate, and strontium sulfate. Fourth, the elements in group 3A, boron, aluminum, gallium, indium, and thallium have oxidation states of positive 3. Examples are aluminum chloride, boron trifluoride, aluminum nitrate, and gallium iodide. Here's where it gets tricky. For group 4A, elements can have either positive 2 or positive 4 oxidation states. Example, carbon has a positive 2 in carbon monoxide, while in tetrachloromethane, carbon has a positive 4. It depends on what the element is paired with. Next, by group 5A, elements have oxidation numbers of negative 3 in binary compounds with metals with H or with NH4+. Exceptions are compounds with a group 5A element combined with an element to its right in the periodic table. In this case, their oxidation states can be found by using rules 3 and rules 4. For example, in magnesium nitride, nitrogen has a charge of negative 3 to balance the 6 positive of magnesium. Also with ammonia, nitrogen has a charge of negative 3. In cesium arsenide, arsenic has an oxidation state of negative 3, since cesium 3 has positive 1 multiplied by 3, so positive 3. Next group. Group 6A elements below oxygen have oxidation numbers of negative 2 in binary compounds with metals with H or with NH4+. If these elements are combined with oxygen or with a lighter halogen, their oxidation states can be found by using rules 3 and 4. In hydrogen sulfide, sulfur has a charge of negative 2. In ammonium sulfide, sulfur has a charge of negative 2 also. Last group. Group 7A elements have oxidation states of negative 1 in binary compounds with metals with H or with NH4+, or with a heavier halogen. When these elements, except fluorine, are combined with oxygen or with a lighter halogen, their oxidation numbers can be found by using rules 3 and 4. In zinc chloride, chlorine has an oxidation state of negative 1, and in ammonium chloride, it also has a charge of negative 1. Well, this is where it ends. We hope you learned a lot about the rules of assigning oxidation states. They're a little tricky, but once you get the idea of it, it will be a lot more easier to do.